I think this is visible to all. This is full screen. Is it? Is it
Yes, sir.
visible?
Yes, it is visible.
Okay, fine. So basically, this is our first unit, basically, which covers the differential amplifier and rod and current current mirror and references, and then operational amplifier. So basically, you must have aware of all the things, but we're going to see what we have seen. Basically, it is a overall unit is a kind of a introduction and review part of that one. So we'll start with the differential amplifier. So why we require this differential amplifier and all this thing we're going to study. So basically, why we require a differential amplifier? Let's say if we are going to consider an amplifier, okay, that is basically an amplifier audio signal from a microphone. So what is happening? We are taking our power supply VC, that is must be a time varying. So whenever it is like that one, then there is a undesirable voltage signal is going to become at the output. That is nothing but a kind of a humming type of noise is going to come. So basically, what is the aspect of this BJT? That is nothing but to amplify anything which is coming there. So basically, rather it is only amplifying the input, it also amplified that what is that humming signal is basically, that is noise is coming. That is why that is what is basically that is a error, a kind of a error. So basically, how we are going to remove this part? Let's say if we are going to have a circuit like this one, let's say where I'm saying this Q1 and Q2 both are say just say now it is a both basically a matched BJT. It means all the internal parameters are similar to each other. So I'm saying that one of the transistor, that is at the Q1, I'm giving us some kind of a signal, and other we are not giving any signal. Basically, it is to the bias only, and along with the bias there is the input at the Q1. So what is going to happen in this case? If I'm going to check at the output at this basically X and Y, basically from where we take a output, or you can say from a basically it is a common emitter type of circuit. So for the common emitter, we basically take the output from the collector end. So if we are going to consider this as the output, what is going to happen? This circuit basically going to come amplify a what a kind of humming noise, and this circuit basically is going to amplify both of the signal. It means the input signal as well as the humming signal, or what is that noise signal. So what is that? This is the equation for the x Vx, where it is saying that we have got the amplified version of B in, okay, which is applied over here at this particular end, and along with the humming noise we are getting at the output. Similarly, at this end, we are getting humming noise. So if I'm going to take the output at this particular, in between this difference, what is going to happen? These two terms is going to be cancel out. So basically, we're going to get the output like this, right? So that is what we say a supply of ripple rejection. So whatever the kind of a humming noise is going to come, that is going to be cancelled out by this particular mean of circuit. So now let's see what is going to happen when the common input to a differential amplifier is going to be applied. So basically, what is going to happen? Let's say at the Vx, we attain this value. Since we are saying that the input at both the transistor has been applied, it means a common input. Okay, it means we'll get a output at the Vx the same what we going to get at the Y terminal, that is what this one. So if I'm going to take a output across these two terminal X and Y, we're going to get a value 0. It means it is saying that it is basically going to reject the common type of a input. Okay, so that is what basically we say of a differential amplifier is very good for the CMRR, that is a common mode rejection ratio. Basically, it is infinite. So that is what written here also. The voltage signal applied to the input node of the differential amplifier cannot be in phase. It means if it is in the phase, it means it's going to be 0. Otherwise, the differential output signal will be 0. That is what both of the signal is in the phase, it means is in the phase as well as the amplitude of the signal is same, then it will going to give you a zero result. Either it should be a out of phase. That is what we are going to see. So that is what differential input. Let's say we have an input voltage signal R 180 out of phase. Then what is going to happen? So since we already know what the common emitter output, it is always giving a 180 out of phase output from that input. Okay. So basically what I am saying, we are giving a positive V in at this Q1 and negative V in at this Q2. Okay. So what is going to happen? We are going to get the voltage across the Vx is amplified version of V in plus Hamming signal, whereas at the Y terminal we are going to attain a out of phase amplified version of V in plus that Hamming. So we are going to, if I'm going to take a means basically a difference of the output, what is going to happen? It is going to get amplified Vx minus V. Basically, this is going to cancel out and this is going to be added on. So we are going to get 2AV V in. So that is what it is saying, that the differential input is going to get amplified rather than the common input is going to be rejected. That is what the utilization of differential amplifier. Now, what is this differential signal can be generated? If we are asking about that, we need a differential type of signal. How we can generate it? Basically, you have gone through the transformer. We basically use what we do. If we going to take a center tape, then what is going to happen? We are going to have a same kind of a amplitude attaining at this end, and that is nothing but a out of phase, 180 out of phase. That is where we can attain the differential signal. And what is going to happen? That is going to have a same DC level. So that is what written here. Differential signals share the same average DC value and are equal in magnitude but opposite in phase. That is nothing but a 180 phase. So a pair of differential signal can be generated among the other way by the transformer. That is what how we can generate a differential signals. So let's see what is going to happen in the single-ended and differential signals. So basically, when we are saying about a single-ended, means we are giving an input at one of the BJT and we are checking out the output. Basically, what is that? That is nothing but called as a single-ended type of a signal. So we have given here, we are attaining the amplified version of this one. And what about the different signal? When we are having what we have already talked last slide, that is how we are going to generate a different signal. This is nothing but by a transformer we can generate, also by a double input op-amp also we can choose. Later on we are going to study this part also, but up to that we are going to see this thing. What is going to happen? We are seeing that if we are utilizing this thing out of phase, 180 out of phase, that is going to give an amplified version of this one. And now if I'm going to check here the signal, if I'm going to subtract each other, it is going to get double of that one. That is what basic thing. What is the difference between the single-ended or differential signals? So till now what we have seen, at this end we are taking a means grounded. So rather taking that grounded, we can say it, we can have a constant current supply, that is nothing but a trail of current. That is nothing but going to give you a elegant and robust differential amplifier. Why we are going to attain this robust one? That is why I'm going to show you how. So since we are saying continuously that Q1 and Q2 are to be matched one, it means the VBE1, VBE2 should be same. So since we have taken this IE along this one, it means that the collector current across the both the BJT will be also going to be same, and that is nothing but a IEE by 2. So by utilizing this one, and I'm saying this is a matched circuit, then if we are going to attain the value at this end and this end will be remain the same irrespective of the input signal. Okay, because you can see it here, there's no any kind of a common mode will going to come. Okay, it means whenever the common mode is there, that is not going to be reflected over this Vx and Vy. That is why we can see with this, with the help of this one, that calculation is going to be easy. And we are saying that RC1 and RC2 is also going to be same. This is nothing but a standard differential amplifier. So now see a differential response, what is going to happen. Let's see what is there. If I'm giving a V in as a +2 volt and V into as a +1. Now we are having a difference of the voltages are there. Okay. So what is going to happen? That is going to change the value at the Vx and Vy. Okay. How it is going to change? So if I'm saying this V in is a 2 voltage. Okay. So what is going to happen? So definitely this is going to be run the current. Okay. Maximum of the current. So what is going to happen? Maximum current is there, and what we are saying that at Vn2, that is +1 volt. So what is going to happen? Basically from this calculation we can see that IC1 will going to be total of the what current we have applied here, that is trail current is totally going to be run from this in. Okay, it means that IC2 will be 0 at this particular point, at this particular point, and due to that one, the Vx is going to be come this VCC minus RCIE, and whereas Vy will be a VCC, nothing but what is the voltage across this terminal. So that is going to reflect over here. So this is a differential response when we are seeing that at Q1 is having this thing, and similarly if we going to change this response, what is going to happen? That opposite thing will going to happen. That is what IC2 will going to become a IEEE, that is a trail current, and IC1 becomes 0, and now this Vy is going to become VCC minus RCIE, where the Vx is become a similar what the potential over here, that is a VCC. So that is what basically happens. Now if I'm going to see how this characteristic is going to be plotted when we are changing the V in minus V into. Okay, so what we are seeing that the current, and we have seen from this equation, basically this equation basically governs this characteristics, and this voltage we have already seen that is okay. Due to that one, what is going to happen? This is the input and the corresponding current, and this is the input and corresponding voltage, how that it is going to change across this particular differential of the output. So now let's talk about the how this virtual ground concept is going to come. So we have already seen how this common mode type of input is going to be deal out. Let's see at the common mode only, we are just changing some plus volt, plus means intermittently, means very small voltage we are changing at the both the input side. We are saying that at Q1 it is plus delta voltage is going to be changed, whereas that at Q2 we are changing a minus of delta V. So what is going to happen, since both are the common, and we are not saying that it is having some kind of a very large difference, so rather going to that one, we are going to see that is only going to be happens. So that is nothing but that is the current due to the plus delta V, and this is what here this current is nothing but minus delta I because of the minus del V. So that is because of that one. So due to this one, if I'm going to check the delta V across this end, that is nothing but going to be 0 only, because what is that overall that we are changing, that is nothing but a 0 voltage we are changing. So that is why if I'm going to see about the delta IC changes across this one, that will be nothing but a, for the case of Q1 it will be collector current will be GM del V, whereas for the Q2 it will going to be collector current will be minus of GM del V. That is what the basically we are going to, if we are going to do for the DC analysis, we're going to get this equation basically. So it means what the mean of it, what we basically from this picture, what I want to convey this thing, rather we are going to change the delta V at this particular A end, or you can say at Q1, or at the B, we are changing minus of del V. There will be nothing that is going to be changed, because we are saying that plus delta V is increasing at this particular end, and similar same value is going to be decreased at this end. So it means at the middle of that one, the voltage is not going to be changed, that will be remain the same value. So there will be no any kind of a change. That is what called as a virtual ground concept basically. Now, if we see about, that is nothing but the base of that small signal differential gain. So if I'm going to check about the current gain across this one, current gain means what is that? What is going to happen? Sorry, current gain, I'm saying voltage gain. What is going to happen? That is the output across the voltage across the output terminal. That is nothing but a 2 GM del V RC. Means across this particular region, whatever the voltage, that is will be this one. And what we have given the input, that is 2 del V. That is only we have given the input. So that is what, due to that one, we're going to get this value minus GM RC. So for the last signal, we're going to see that equation is going to come like this one. We need not to so much worry about the last signal analysis, because it is not there in our syllabus. So basically, I have written because you should know about that, how does basically work for the large signal analysis. Basically, that is not usable for us, but for the electrical domain. So now I'm not considering that part. So now, if I'm going to look overall at how this input output characteristic is going to be look around. So basically, this is what for the input voltage across that one, how this current is basically varying across the differential of the output. And this is what, how this voltage is going to change across the output terminal. And this is what the overall aspect of that input and output voltage. That is what the output characteristic basically will say. Now, when we are going to analyze the operation, we need to check about that all the things is going into the linear region. Otherwise, there will be a distortion is going to become across that one. And how basically comes when we say that amplifier operating in a linear region, means it is working within a limit of a 1 or 10 millivolts only, then only it is going to happen. But that is basically depending on the GMRC value. So if it is becoming very higher, that makes the transistor go into a cutoff region or the out of the active region, then what is going to happen, or you can say a saturation region, that is nothing but this is going to be happen. We are getting a clipped version of the output, not the amplified version. That is why we need to check every time. It should not be beyond the limit of that output range. Okay, that is what we need to check about that one. So that is what all about the linear and non-linear region of operation. Now comes to the small signal analysis. So when we are going to draw a line across this one, and if we are going to try to make the small signal of the left hand side and right hand side, we're going to have this equation, this particular small signal analysis. If we going to look into this one, both are going to be similar fashion we are going to get. So if it is happening, since at the P, what is going to happen? This is nothing but a P. This is the P point. So when we are going to see a small signal analysis, this is nothing but a constant current voltage. Constant current source. It means we are going to replace with the internal resistance, that is nothing but going to be an open circuited. So that is why what is going to happen? We can replace this like this one, and we can make the circuit like this one, and that is nothing but also a representation of this thing. So since that one, we can say that for this kind of circuit also we can get the similar result, as we have already in the beginning of that one. We are always looking for this one. What is the advantage of that one? We are just keeping the constant current, so that is why we have come to the trail current type of structure. So that is what half circuit, what we have seen, what we have done, that is nothing but called as a half circuit. That is one of the example. When we are giving a constant current source, what is going to happen? When we don't have a RC there, then it is going to replace by the internal resistance of that both of the transistor, that is nothing but R01 and R02. And since both are the match, it means R01 and R02 will be a same one. That is why we're going to get this value. Similarly, if you're going to further extend this value, what is going to happen if I'm going to utilize this type of circuit? What is going to happen if I'm going to make another half circuit of this one? Then what is going to happen? We already know about this, right? So whatever is there, that is going to be go into the parallel of that one. If I'm going to make a equivalent circuit of this one, what is going to happen? R1 parallel to Q1 means internal resistance of this Q1 transistor and the internal resistance of this one. So that is what nothing but going to become in the parallel fashion. So we can represent the voltage gain like this one. So since due to this one, we can also rearrange this particular format in this way, and this is nothing but going to give you the same kind of result. And there are several examples, and now here we can see that if we have a different of RE is there, what is going to be, how this circuit is going to be changed. So nothing but we are going to get in the denominator term, that is 1 by Gm plus RE is going to be C. So we have already gone through that, how this basically a differential amplifier is there and how this basically a calculation is occurring. So basically what is that? The function of the differential amplifier is nothing but to amplify the difference of a two signal, and that need of the differential amplifier is many physical measurement arises where the response from a DC to many megahertz is required. It is also a basic input stage of the integrated amplifier, op-amp basically. So basically, if you're going to say what is the building block diagram for this one, that is nothing but is going to be represented like this one, where the two inputs are there and the output will be V0 and its output will be, and this is the internal structure of that one. So if I'm going to say about the output is going to be represented like that one, that is nothing but the V0 is directly proportional of the difference of the two inputs. That is the two input signal, and this is the single ended output when we are going to see single ended output. So this is what when we are saying about the differential gain, that is going to get like this one, where the AD is the gain with which differential amplifier amplifies the difference of the two signal, and hence it is also known as differential gain of the differential amplifier. That is nothing but AD is equal to V out by VD. That is nothing but we have already seen how it's going to come this thing, minus Gm RC, where the VD is nothing but V1 minus V2. When we are going to talk about the common mode, it means that time the VC is nothing but V1 plus V2. Okay, and the differential amplifier also produces the output voltage proportional to the common mode signal. So is there any kind of a common mode type of signal is there, we are going to get the attain the value V out is equal to, if we are going to talk about the single ended type of output. So that is what we are going to attain, where the AC is nothing but minus RCB RE in a common mode gain. It means where the V1 is equal to V2 due to the common mode gain AC. Hence, overall, if I'm going to talk about the output, will be along with the common mode as well as the differential, we're going to give you this kind of a result, that is E naught is equal to AD VD plus AC VC. Now come to the I have already taken this name, that is the common mode rejection ratio. Basically, what we do, it tells that common mode rejection ratio is going to be a very high, because what is going to happen, we that is nothing but the AD by AC. So we already know about the differential gain is higher than the common mode gain. So that is nothing but going to be get GMRE. And if you're going to represent in the form of the decibel, that is nothing but this equation is given below that one. That is also short name, that is CMRR. Class, I'm Shivam Pandey. Am I audible?
Yes, sir, you are audible.
Yes, sir.
Yes, sir.
Okay. So we are at this particular slide. Sorry for the interruption of the internet. Actually, light has gone. So again, starting from this point. So input and output resistance is going to be come for the differential mode input resistance, that will be Ra is equal to 2R of Re, and differential
Sir,
output
you are
resistance will be nothing but, hello.
sir, we are not able to see the screen actually.
Okay, let me wait a minute. Is it visible now?
Yeah, now it's fine.
Okay. So basically, this is the input and output resistance. That is the input resistance, that is nothing but a 2 of Re, whereas the output resistance will be Rc by R naught. So now comes to the MOSFET type of a differential amplifier that is given here. I'm not going to so much detail of the calculation how we have get this thing. This is already we have done it in the previous years. That is when we are studying the analog circuits. So basically, I'm not going to go into the detail how we have calculated these all things, as we have already done for the BJT. I'm not going to go into that deep one. So basically, when we are going to calculate this differential amplifier for the case of a FET, we're going to get the value for the differential gain, that is GM RD, and for the common gain, we're going to get a minus of RD by RSS, where the CMRR will going to come GM by GM RSS. So similarly, if I'm going to look around the basically a half circuit, what is going to happen? We can see similar kind of a structure. In the common source, like it is not going to work for the basic. So now we keep track of two output, that is two, because there are several ways to compare one circuit. Identical means of that, what is will have each two will be similar. If I go to look around this one, since it is having a kind of a ratio to that one, we're going to have this structure and we as well for the type of operation kind of a game. The small and have calculated the node voltage 0, 1, 2, what should be solved, find Q. So since it is a lengthy, that's why I've given already that all equation given here. Because the circuit is / common mode method is and we can use configuration formula. We can achieve these all equations. So mode in this case, what is that? Equal to 0 is it plus okay, method, and there is a similar and if we parallel we do so half circuit. We get if I'm not going to give RSS, two RSS, then we won't get the same kind of a result. That is why we can make a half circuit, identical half circuit in this way, okay, which is not same in the BJT. So this is the difference between the FET and the MOSFET, FET and the BJT. Now comes to the difference mode when we are saying that VC is not a 0, when we are saying that V1 is equal to minus of VD by 2, where the V2 is plus VD by 2. It means we are saying the VGS1 is equal to minus of this VD by 2 minus V3, whereas that VGS2 will going to become VD by 2 minus V3. Okay, this is what the VGS1 and VGS2. And similarly, we have calculated the value for the different nodes. Okay, different node means this point, okay, and this point and this point. Basically, we have done it calculation. And to find out the value for the node 1 and node 2 and node 3, by rearranging, what we're going to get? We're going to get the possible solution for that one. V01 plus V02 is going to be 0. It means that it is going to get a out of phase of value, where the V3 is 0. Now, what happened when we're directly taking we directly taking the output this one, and we are saying that V3 is a 0, then how we are going to steer apart for the case of differential amplifier, differential mode, we can clip down this thing in this part rather taking the RSS. Okay, in that case, we are going to attain the value these ones. So because the symmetric differential mode circuit also break into two identical half circuit, okay, in this format. Check it out whenever you are making a half circuit, need to check about the differential mode and the common mode. And that depending on the differential mode and the common mode, we'll see that resistance value is basically changing. So this is how we have converted a half circuit for the case of the common mode and differential mode. So in the case of common mode half circuit, current about the symmetry line are equal and the voltage about the symmetry line are equal. It means V01 is equal to V02 and no current across the symmetry line basically in this particular line. That is happening in the case of a common mode half circuit. Whereas for the case of a differential mode half circuit, what is going to happen? The current about the symmetry line are equal in value and opposite in sign. Okay. Whereas in the case of a voltage about the symmetry line are equal in value and opposite in sign. And the voltage at the symmetry line, at this particular line, it is going to be 0. That is what basically happening in the differential mode. Now constructing a half circuit, further we can do like this one. If we have a circuit like this one, when we are changing the below that resistance with the help of a current source, then we can do like this one. In this way, we can generate a half wave circuit. And again, keeping in mind whether it is for the half wave means common mode format or the in the case of a differential mode. Okay. But we have seen that there is a difference when we are taking a resistance, but in the case of here, what is going to happen? There won't be any kind of a resistance, so it will be very easy for converting into a half circuit. So if we are going to see for the common mode half circuit, no current crosses the symmetry line. Okay, no current crosses the symmetry line. It means what is going to happen? The circuit is going to be steered like this one, and we are going to get the value of V01 is equal to V02 when we are keeping the collector constant. Oh, sorry, common. So for the case of differential mode half circuit, how are we going to generate this one? See the difference. This basically is going to be not there for the case of differential type of a thing. And for the case of differential, we are going to attain the value like this one. And see, half circuit work only if the circuit is symmetric. That is what showing here. Okay, so half circuit for a common mode and differential mode are different. bias circuit is similar to the popular one and this thing, because they are much less sensitive to the noise. Less sensitive means it is rejecting that noise. And biasing, relatively easy direct coupling for off stages. Biasing resistor does not affect the differential gain and does not need a bypass capacitor. Okay, as we can say a conventional type of amplifier, we require a what kind of a, we require a coupling capacitor and all this thing to amplify the gain. Coupling capacitor. Rather than that, we can do with the RSS and all. So that is what it is saying, that no need of a precise biasing and gate in the IC. This amplifier is also why are value useful. A major goal is to minimize the noise level that we have already seen. By that one, what we are going to do, we are going to achieve from any source like thermal, electromagnetic waves and all. That may be a thing. So basically, a regular amplifier amplify both signal and noises. Okay. Yeah, and we use the signal is amplified a lot more than a noise, which improves the signal to noise ratio. That's what we have done. So we are saying that V1 is like this one and V2 is like this one, where the V noise is there. So if I'm going to take a differential of the that one, we're going to get only the V. Okay. Better result. This one, if I'm going to see that for the differential gain output and common gain, that is not going to give you a CMRR value. So if I'm going to see something to identify common, so differential where it is connected. So now, if I'm going to look into this one half circuit of this part, that is going to, for the case of differential amplifier, it is look like this one. Okay. Rather, for the common mode, what is going to happen? You can see differential mode is looking like identical, where in the case of a common mode, it is not going to be identical. Why so? Because this comes into the picture due to that one. This, for the case of common mode, it cannot be when we are going to use two common source amplifiers. And on that often this and the sub-review which we have already seen. Now, configuration of differential amplifier stage in the op-amp can be based on the configuration. Core configuration, that is the dual input balanced differential amplifier, dual input unbalanced output differential amplifier. Third one is single input balanced output differential amplifier, single input unbalanced output differential amplifier. and the circuit will going to be look like this one. For the case of dual input balance output differential amplifier, we can see that there's a dual input here and here, and as well as balance output, that is nothing but a balance one. Due to that one, it is called as a dual input balance output differential amplifier. See, this is a dual input unbalanced output because we are taking the output from a one hand only. So that is what dual input unbalanced output differential amplifier. And this is the single input balanced output differential amplifier. We are giving at the only one of the end, we are giving an input, other end is grounded, whereas we are taking a difference of the output, then that is what called as a single input balanced output differential amplifier. Similarly, single input unbalanced output differential amplifier, when the one of the input we have given the input value, where the other is grounded, and we are taking the output from a one hand only. That time it is called as a single input unbalanced output. Okay, that is all about the differential amplifier. Now we are going to see what are these current mirror and references. Basically, current mirror is nothing but it is going to replicate a kind of a current at one particular point to the another end. It means similar kind of a current is going to be obtained at different point of that circuit. So that is what definition of the current mirror is. A current mirror is a circuit designed to copy the current through one active device by controlling the current in another active device of the circuit, keeping the output current constant regardless of the loading, resistance or whatever the load. It doesn't affected by the any kind of resistance applied over the another end. That is what basically called as a current mirror. It is a circuit that outputs a constant current that is equal to another current that is nothing but reference current. So what is the current source? The current is independent of the load resistance. The current is not influenced by the supply voltage or the temperature variation or other operating condition. Basically, this is what the called current source. And what the mean of current mirrors? Generate a DC current in direct ratio with the reference current used to bias integrated circuit. Basically, that can be generated by the two ways: the current source and the current mirror. That is by the MOSFET as well as the BJT. So let's see. So basically, this is a basic current mirror circuit, where we have seen that both for the making of current mirror, the same thing is there. Both the transistors is to be matched, but rather that one another condition is that what is that? That is the Q1 is to be in a matched one, and what is going to happen? This one I reference is going to be come to be same as the I out. Okay. So the collector current is given by this equation, that is IC is equal to beta IB. Since we are saying the both are in the saturation region, so since two transistors is identical, so I reference will be nothing but the IC is equal to 2 IB. Okay, that is only the thing. This makes the output current, that is I out is equal to IC. Since base current is small compared to the collector current, we can assume that the I output is nothing but similar to the I ref. That is what the way we can replicate the current. That is what also current mirror. So what is the basic principle behind this one? The current mirror uses the principle that if the gate source potential of two identical, we are going to go from the MOSFET to the BJT. That will be very easy to understand the current mirror basically. That is why I'm going to go like this one only. So current mirror uses the principle that if the gate source identical of the two identical MOS transistor are equal, then the current flow through the drain terminal should be the same. Okay, So NMOS current mirror are used as a current sink, where the PMOS current mirror basically used as a current source. Sink means which is going to be sink all the things basically. That is what the mean of it. There is a variety of current mirror circuit available, each of them having their own advantages and application. We're going to see that one. So for the case of proper operation, the output terminal, that is the drain of the Q2, drain of the Q2 must be connected to the circuit that ensures that Q2 operates in the saturation region. That is what basically says. It means this should be connected in a fashion, they should be also in a saturation. Now comes to look into the mathematical term, how we basically attain this current mirror, how we can attain this thing. So basic concept is that we already know about the equation of the saturation region. That is nothing but this half Kn W by L into Vg minus Vt a whole square. That is what the thing. But we can also represent the ID, nothing but KVL across this region, we can get this equation, that is Vdt minus Vgs by R. Okay. So we can get the ID current. Okay. Similarly, I naught saturation, we can say this thing. And if we are going to divide these two currents, will attain this thing. We can attain this thing. It is nothing but it is depending on the W by L ratio basically. And if I'm going to say this W by L of both of them is similar, so we can attain that same kind of current. Okay, so we can also change the ratio of the current to be transferred basis on the W by L ratio, or you can say a aspect ratio. So that is what current scaling. Okay, now let's see. We have made this connected part. This is nothing but the one of the part which is required for the current mirror. So where we are saying that it is having a 3 W by L ratio, where the current is coming like a 0.3 milliampere, and it is connected to this two FETs. Okay, then what is going to happen? Which says that the I1 is nothing but a, what is going to happen? It is going to, I1 is nothing but I1 is equal to, what is going to happen basically? IREF. Okay, I need to take the this pen. Basically, what is going to happen? I1, if I'm going to say I1 is equal to nothing but the IREF into what is that? W by L of the 1 I1 by this IREF. It means 0.3 divided by 3 into what is that? 2. It means that is going to come like this one, and similarly this is going to become for the particular current across this particular region. This is how we can basically scaling of the current, we can done it. Now comes to the basic concept of a current source and a current sink. So basically, whenever we are designing with the help of an NMOS, we design a current sink. Whenever we design for the case of PMOS, it is always behave like a current source. So this is how PMOS means source. Okay, this is what we have sandwiched this basically a drain to a gate. Okay, drain to a gate means we are design a current mirror, and this current mirror nothing going to be behave like a source. and where this is going to be behave like a sink because it is continuously draining through a ground. So this is nothing but a NMOS is going to be say as a behave like a sink, and this is behave like a source only. Now let's see what is going to happen on the V0 on IO. Okay. To ensure that the Q2 is saturated, the circuit to which the drain Q2 is to be connected must establish a drain voltage V0 that satisfies the relationship, that is nothing but this thing and this thing. Okay. And the channel and modulation can have a significant effect on the operation of the current node. That may be noted down. Okay. It may change whenever there is a channel and modulation is there. But we are right now we are not considering that part. Basically, for that case, what we need to do, we need to check out it should not go into the channel and modulation case. Okay. So as V0, so as V0 increases, the I0 will also increases according to the incremental resistance R0 of the Q. So basically, if you want to equation, early voltage basically. Okay, so if the early voltage is there in the comes into the picture, that equation is going to govern. Okay, that is 1 plus V0 minus VGS by VA2, that is this one, the early voltage. So whenever the channel and modulation comes into the picture, that is going to be happen. Now comes to the current steering circuit. It means that is nothing but same thing. If we are having a same kind of a concept of a similar match type of transistor is utilized, then we can see steering circuit is going to become. If two different type of MOS's current mirror is there, then we can say this particular thing is going to be work as it can be applied to provide a DC bias and load current for the various amplifier stage in the IC. Okay, let's say Q1 and R determine the reference current. Okay, and saying Q1, Q2, and Q3 forms the two output current mirrors basically. See, so this is Q1, Q2, Q3 forms the current mirror. Okay, so it means the current which is coming here, that is also same here also, I3. Okay. So if I'm going to look into the picture, I2 is having equation this one and I3 is going to be equation this one. So depending on the aspect ratio, we're going to have the value across this particular drain current we're going to come. So to ensure the operation in the saturation is the voltage at the drain of the Q2 and Q3 are constrained, that is, it should be like this one only. VD2 and VD3 should be having this saturation region of a condition. Then only it is behave like a current mirroring is there. Okay. So rather we utilize this circuit directly in our current mode circuits. Okay. This is the base of the current mode circuits. So we are saying that we are not going to directly utilize this circuit. Rather utilizing this circuit, we utilize this thing for a constant current in the case of a current mode circuit. Okay, this is the base of the current mode circuit. Now come to the calculation of all this thing. Current I3 is fed to the input side of the current mirror formed with a PMOS. These are the NMOSs. These are the NMOSs. This is nothing but NMOS means We have already seen NMOS is basically a sink, okay, and PMOS are the basically behave like a source. So that is why we have designed this circuit. And to okay, and this is nothing but the basis of the current mode circuits. Okay, so let's see. Transistor Q4 and Q5. This is nothing but a mirror provided by the I5. Okay, mirror provided by the I5. Okay, to keep the Q5 in a saturation, the drain voltage should be this. We already know by the conditions. Since this I4 and I3 in the same hand, so it must be same. Okay, if it is same, it means it is going to govern the current of the I5. So while Q2 plus its current I1 from the circuit, Q5 pushes its current I5 into a circuit, and thus Q5 is appropriately called a current source, whereas the Q2 should be more properly called as a current sink. As I already told, this is nothing but going to be NMOS is basically work as a sink, and this is basically work as a source. That is what basically occurring. This is what overall that we have seen, that is what called as a FET type of a current mirror. Now comes to the BJT current mirrors. It is also similar like a structure we are going to see. What is going to happen here? If you are going to sandwich this particular, this is nothing but what? Collector, and this is emitter, and this is the base. So if you're going to sandwich the collector and base, it means it is saying it is going to active region basically. And similarly, this should be also work in the active region. In the fashion, we need to arrange that part. It works in a fashion very similar to the MOS mirror. However, the two important differences are there. Non-zero base current of the BJT. In the case of FET, what is that? The current going inside this is current is not going to be zero. It takes part in that one, okay, for making the current. So how we are going to achieve the current mirror using the BJT, we're going to look into that one. So this is what cause an error in the current transfer ratio of the BJT mirror. So the current transfer ratio is determined by the relative area of the emitter base junction of the Q1 and Q2. So that is why we say this Q1 and Q2 should be matched. If it is matched, it means the emitter base junction, or you can say area of that one, is going to be have similar one. Then we can achieve a similar kind of a basically a base current, and accordingly we're going to get a same kind of a collector current. Let's see how we are going to attain. Case one, let's say beta sufficiently high. Beta sufficiently high means the current going inside the base will be zero. So we can neglect the base current. So the reference current RF is passed through the diode connector resistor. Basically, this is nothing but a kind of a diode connected transistor, because we have sandwiched the base and the collector, and thus establish a corresponding voltage VBE. So it means that is nothing but this is also VBE, because it is attaining across this one. Okay, which is term is applied between the base and emitter of the Q2 also, which is nothing but similar, which is occurring for this part also. Now, if Q2 is matched with the Q1, more specifically, we can say emitter base junction area of Q2 is the same as that of the Q1. Then the Q2 has the same scale current. If the area is having same, it means the scale current is also same as the Q2. Then the collector current of the Q2 will be equal to that of the Q1. Okay. If it is there, then the collector current will be same. So due to that one is we are going to attain this value. And how basically we can achieve mathematically, we can say that to obtain the current transfer ratio other than the unity, say M, we simply arrange that the area of emitter base junction of the Q2 as a M times of the Q1. In the case, we'll get a value like this one. And mathematically, we can represent like this one, I0 by IRF is equal to IS2 by IS1. That is nothing but depending on the area of the emitter base junction of Q2, emitter base junction of the Q1. And if you go into detail of that scale current, we're going to come into this one, which is not required right now in this particular subject. We need to go into this whole detail of this, what is going to happen. Basically, that is nothing but a constant current for us. But for the depending on the area. Depending on the area. And all the thing is matched in this, we can have the same kind of scale current. So, but when we are talking about the B is very high, then only we are saying about this thing. It means alpha is equal to beta by 1 plus beta. Other things, what is going to happen across that one? That means if it is happens like that, both are the high. It means it is going to be coming across like equivalent to 1. It means alpha is equal to 1. It means I is equal to basically IC. And due to that one, we are going to attain the same value throughout this region and this region. Okay, because this is I is equal to IC plus IB. Now let's see about the case 2 when there's a finite transfer beta on the current transfer ratio. Now let's see. Basically, if we're going to look into the IREF, if I'm going to check about this value, what is this? This is nothing but what is that? IC, this current plus whatever the current here. Okay, whatever the current here. And if I'm saying IC is this one, then the current across this is nothing but the IC by beta. IC by beta. Okay. And if I say this is nothing but my IC, then it should be a divided by 2 because if I'm saying that Q1 and Q2 are the same. Okay. So it is going to be divided. So if it is so, and if it is so, like that one, then this is I0. Okay. Now if I'm going to divide in both the current, what is going to happen? We'll attain the value like this one, that where the I0 by IRF is going to come like the 1 by 1 plus 2 beta. And similarly, if I say it is having a ratio of is area of emitter base junction having a ratio of M, then we can represent it like this, the generalized formula for the when the beta is having a finite value. So this is what the value. And if we are going to further consider the consider the early voltage effect, okay, then what is going to happen, which is going to become overall the generalized value for this thing. And if you want to make a current mirror, what we need to take, we need to nullify this particular, or you can say make it the value 1, then it is behaving like a current mirror. So that is what all the basic part of the BJT current. If I'm going to look into that one, it is depending on the emitter base junction. And if we see, we can say the core equation will be this one. And if the beta is finite, we're going to get the value like this one. And if we have an aspect transfer ratio of that one M, then we are having the value like this one. And if you're considering the early effect, then we are going to have a equation. Okay. Now let's see what is there in the BJT steering circuit. Means how it is going to steer in the case of BJT. This is similar like a fashion what we have seen already in the FET cases. Okay. So basically two parallel resistors. So double current will be there. So double current will be there. Since this is a already we have seen this is a nothing but a current mirror. Okay. IRF is going like this one, then this is also having the same kind of a resistance. So here if it is a triple, it means a triplet of the current will be there. Same way as the for the case of NMOS, that is behaving like a sink, okay, and PMOS behaving like a source. Here also that this basically a PMP, PNP is behaving like a source. Class, this slide is visible to you all. Just somebody just tell me whether this slide is visible to you all or not.
Yeah,
Not
it's
visible.
visible.
Okay. Because of the internet issue, again it has happened. So I'm sharing again. Okay. Now is it visible? I think. Is it visible?
Yes, sir.
Okay. Simple current mirror for the case of a BJT, improved performance. We do see basically current is also going to affect the current ratio. Basically, the temperature dependent. As so, in the case of BJT, we need to take care that the ratio should performance based current mirror. So that is what we're going to look around this one. To performance need to be addressed. The accuracy of the current transfer ratio suffer particularly from the beta, finite beta of the BJT, and output resistance, which is in the simple circuit, is limited to the R0 of the MOSFET. The improvement is going to see in the cost of MOS-based circuit. Current compensation, we're going to look into this basically in this slides. The cost code means we mirror. Basically, we have cost coded the another mirror basically. That is basically same advantages because we're going to improve it. So that is what written here, that the connected Q1, which forms a basic mirror between a Q1 and Q2, is another diode connected transistor. Q4 is used to provide a suitable bias voltage for the gate of the Cosco transistor Q3. Okay. So to determine the output resistance of the Cosco mirror to drain of the Q3, we assume that the voltage across Q1 and Q4 are the constant. That is nothing but across this one and this one. We assume to be that is having a same. Thus, the signal voltage at the gate of the Q2 and Q3 are 0. Thus, R0 will be that the Cosco current source formed by Q1 and Q2 will be going to like come like this one. And minimum voltage of VT plus 2 overdrive will going to become. Now, what is there in the case of a BJT? We have seen we are going to see that bipolar mirror with a base current compensation. What we need to do? We need to come out of this beta factor. So if the beta factor is lesser there, and that is not going to affect the current transfer ratio. That is what we have. Like this. Okay, attaching section. Okay. EC minus E3. That is what? This is the VBE1. Okay. And this is nothing but plus minus VBE3. Okay. So that is what going to come. If we are keeping some resistance here, then it is going to come. So if it is like this one, you can see it here. We have already divided this one. I have to discard this thing, then we can. Okay. So you can see it here. When I'm keeping the IC, if I say the current going inside this resistor Q1, I'm supposing this is IC. If it is IC, it means this current will be IC by beta. Okay, and this must be also IC by beta because it need to be matched to 1. Then only it is going to be work properly. If it is same, then only we can achieve this current. This is our aim. So this is what we required. Okay. So if it is there, then what is going to happen? The current across this particular hand will be 2 IC by beta. And if it is like this, then we can say the current going inside this one will be 2 IC by beta into. I think again it is not shared. Now again I'm sharing. No? Now tell somebody, is it visible?
Yes.
Yes, sir.
Yes, sir.
Okay,
Visible.
fine. So I was telling about this couple, basically this current. What A lot of internet issues are there. Okay, so I was telling about this thing. If I'm going to represent this REF now, if you're looking at this point, what is going to happen? That is going to come. This equation will be like this one. So now if I'm going to look into the transfer ratio, we'll get this one. And if it is going to come like this one, so 2 divided by any higher value, 2 divided by any higher value, it means it is nothing but very high. If I say it is a beta is equal to 50, then 50 square means it is going to be a 2500. It means a very high value. So 1 divided by 2500, it is almost going to give you a 0 type of a value. So basically, we can directly say it is get rid of basically a beta factor, which means that the array due to the finite beta has been reduced from 2 by beta, which we have already attained in the case of a simple mirror. Now we are getting 2 by beta square. That is a tremendous improvement. Unfortunately, however, the output resistance remain approximately equal to the I0. That is in the case of simple mirror. So basically, we can say in a nutshell, we have attained this thing, but although we have not attained the output resistance case, still the same. So that is what again we required some kind of advancement to achieve the problem in the case of the output resistance. That is what we have go into a Wilson current mirror. So in the case of Wilson current mirror, what we have seen, what we have done it, we have made a structure like this one, and if I'm going to look into the mathematical term, what we are going to see here, we are getting in the value directly like this one, rather in the case of the beta square plus beta, there is no another single means term is going to come. So this is what their factor is there. But what is going to happen in the case of this one, when we are going to calculate the R0 across this one, what we are going to attain, the R0 is equal to Vx by Ix. So if I'm going to calculate from here the equation, this is a mathematical term which we have attained, that R0 is going to come like the beta 3 R0 3 by 2. It means going to be changing the value, that is nothing but depending on the beta 3. Okay, it means it is attaining a higher resistance, output resistance value. So the output resistance is going to be come like this one for the case of Wilson current mirror, and similarly to the bipolar Wilson current mirror for the case of a FET, we also going to get this value. So in the case of Wilson current mirror, we are achieving this advantage. So that is what both are the very improved version of the current mirrors. Now comes to the why we have already attained all these things, then rather than still we are going to another current mirror, that is what called the Wildelar current mirror sources. Why? Because when we are talking about the current to be generated in a very minute value, okay, then we require a very high resistance value at this particular end, to minimize the current across this one. Let's say if I'm giving a 1 milliampere type of current, and we are attaining, I want to attain a current here as a microampere, then we cannot achieve with the very less value of resistance. We need to have a very mega ohm of type of resistance. That in that case, we require this kind of a circuit that is called as a Whittler current source. It is differ from the basic current mirror circuit is an important way a resistor RE is induced, or you can say included in the emitter lead of the Q2. Neglecting the base current, we can write this equation for the case of this one. Okay, for this end, basically, if I'm going to write. So similarly, VBE2 will be this way for the case of this one. And if I'm going to compare this VBE1 with this one, what are we going to get? We are going to get a VBE1 minus VBE2, that is nothing but VT NL REF by R naught, because if I'm going to subtract these two, what is going to happen? Scale current is going to be get down. So okay, but we also note that VBE is nothing but equal to VBE2 plus R naught RE. That is nothing but a voltage drop across this one. That is nothing but R0 RE. So that is, we also know this thing. So if you are going to compare R0 equal to VT ln REF by R0 by RE. This is a basic concept where this RE is going to come in the picture of the current transfer. So in that case, what is going to happen? Whittler current source provide an area efficient way to implement a low valued constant current source. That is also a high output resistance is also going to be achieved in this case. That is what the advantage of the Whittler current source. So Whittler current source allow the generation of small current, usually relative to the small resistance that I have told you already. For the case of simple resistance, simple current mirror, we require a very high resistance to attain a small value of the current. Rather, in the case of Whittler, we don't require. So that is what the advantage is in the comparable or the same in the chip area for the integrated circuit. For the high resistance, required a high area. So if you look into this one, what is going to happen? If you want to vary a small output current, then the resistance required will be very large. That is what this resistance required, very large value. So where in the case of Whittler current, what is going to happen? It allows generation of small current using a relatively small resistance. How it is going to happen? Basically, we have already seen that this is what happened. Okay, this is what happened. So we have already having the RE, although we are giving a same kind of a resistance, but we can reduce down the current across this I naught with the help of RE basically. Okay, this is how basically happen, and as well as the output resistance is going to be comes into the picture because of this RE. It is going to be improved. That is, we are attaining the R0 equal to 1 plus GM3 RE parallel R pi into R0. That is what basically happens. So I think this is all about the current mirrors. And so I'm thinking to pause it now here only up to the current mirror, because the next is going to be, I'm going to look for the current referencing and the voltage referencing type of circuit, which I'm going to cover here. So I'm going to end up here only. So next Saturday or Sunday, we're going to slot another lecture. So up to here, it will be, I think, okay. So just go through this one. I will share this PPT in the group and go through this particular PPT. And rather than this one, I have already shared this this particular syllabus in the group or not? Just tell me somebody. Did I share that syllabus of the subject?
Sir, please share once again.
Okay, I'll share it. Within that syllabus only, that name is already there. For this particular what right now it is going on, you can go refer any kind of analog circuit books. Okay, not an issue. But when this basically a current mode approach is going to come, that time you need to follow this particular book only. Okay, Tomoji, that is nothing but a current mode approach. So I'm going to share this part in the PPT as well. I'm going to share the PPT as well as that syllabus. So those who are not there, they can go for this particular video. It will be there with this link only.
Okay, sir.
Okay, fine. And hanging up now.